our first official speaker for this afternoon is Professor Michael Fuhrer. He is an ARC Laureate Fellow and Director of the Monash Centre for Atomically Thin Materials. His research group explores the electronic properties of novel atomically thin materials such as graphene, layered transition metal, and I hope I get this correct, dichalcogenides, and layered topological insulators. His research goals are to understand the mechanisms of electronic conduction in these materials and how they can be exploited in the development of future low-power computing devices. Thank you.
Okay, thanks. Thanks for coming out in this. The weather's not very good, I must say. So, okay. So I'm going to try to do a couple of things. I'm going to try to tell you a little bit about graphene from a physicist perspective and why it's interesting, and then some of the other interesting aspects of graphene and other atomically thin materials. And then I'll tell you about this Monash Center for Atomically Thin Materials that we have recently put together. So. To understand the history of the graphene revolution, we have to go back to where graphene comes from. So graphene is the substance that makes up graphite, which is found in for instance, the lead of your pencil. So if you write with a pencil on paper, what's peeling off of the paper are multiple sheets of graphite. And what was really interesting is that a couple of researchers found that if you use very sophisticated tools such as Scotch tape, tweezers, you can make this process. You can take this process down to an individual atomic layer. And so what was necessary actually was a way to visualize these layers, and in fact you can visualize them if they sit on the right substrate. And so this is silicon dioxide on silicon, and you can see single layers, bilayers, etc. And so this, what this enabled immediately was the ability to make devices that looked like transistors, so electrodes on single sheets of graphene. And experiments on devices like that led to the Nobel Prize in 2010 for Andrei Geim and Kostya Novoselov, who came up with this technique. So I think if that was the end of the story, there wouldn't be much to say, because Scotch tape is not a manufacturing technique. So, but these days, once you show something's possible, people will go out and find lots of ways to do it. So you can grow graphene epitaxially on silicon carbide over wafers that are 100 millimeters across. You can grow graphene on copper and transfer it onto plastic substrates and have single sheets of carbon that span 30 inches across the diagonal. So now we know how to manufacture these things, and these techniques are growing. So a little bit about the electronic properties of graphene. Maybe one slide on why it's interesting. So typical semiconductor materials that we might be familiar with are materials that have a band gap. So that means that there's some conduction band, some valence band, terms you might have heard, and then there's some energy gap between them. If we look at the states in graphene, we can also identify a conduction band and a valence band, but these bands actually touch at some very special points. And it's the touching of those points and the fact that graphene has no band gap that makes it special. So what this means, the way you can think of graphene is you can think of it as a semiconductor with a band gap that goes all the way down to zero. So the limit of a small band gap semiconductor. And so that's useful. It means graphene can actually be used for things like transistors. It can be used as a photoconductor. It can be used as a sensor. Graphene also is in some sense a metal. It doesn't have a band gap, so it always conducts electricity, but it's a metal whose properties are in some sense tunable. We can change the conductivity of graphene, and there are things that we can do to alter its metallic conductivity. So it's useful as an electrode. It's useful as a transparent conductor. It could be useful as an interconnect. So electronically there's a lot of things that graphene is useful for. Happy to talk with you lots more about that. It has other extraordinary properties, and I think this is why it's thought of as, in some sense, a wonder material. Not only is it a great conductor, so it has the lowest intrinsic resistivity of any material, lower than that of silver, but it has incredibly high thermal conductivity. It has incredible mechanical strength. It's the strongest known material. High surface area, high current carrying capacity. It's optically transparent, so it has a number of interesting properties, and many people are exploiting different properties, and some of those people are here in the room. So it turns out that graphene is actually one of a class of materials, and so that's something that has been realized, that there's not just graphene, that there are other things. Graphene, of course, is the component that makes up graphite. It's atomically thin layers of graphite. There are other layered materials. For instance, molybdenum disulfide, or molybdenite, is a naturally occurring mineral. And so this is actually a little chunk that was mined in Queensland. And one can disassemble that chunk into atomically thin layers, and we have in my lab. And you can make transistors out of it that are actually quite good. It's a semiconductor, unlike with a sizable band gap of about 2 eV, unlike graphene, which has 0 band gap. So there are other materials, topological insulators, which are kind of a weird physicsy thing, and they're also layered materials. So and more. There's phosphorine, silicene. There are other layered materials that all have interesting and unique properties. So to capitalize on this, we've formed this Monash Center for Atomically Thin Materials. This is really an interdisciplinary effort. It spans a range of disciplines. I think it's on the next slide. So we have researchers in physics, in materials engineering, in chemistry, mechanical engineering. So we're looking at a range of different properties of this novel class of materials. Most of it at this stage is graphene and graphene oxide, because those are the materials that have progressed farthest along the chain of knowledge and science to technology, but we're interested in other materials as well. I should point out Dan Lee will be talking later, is the co-director of our center, and Tiklam is in the back as our center manager. So these are other good people to talk with about the center. So the areas of interest really span from theory and modeling of these materials, understanding their properties, maybe electronic or mechanical or chemical, synthesizing new materials, characterizing materials, and there's a variety of characterization techniques that can be found here in New Horizons and within the center. And applications, and those span from electronic applications to energy storage, sensing, filtration, membranes, water remediation, et cetera, et cetera. So and some of them you'll hear about tonight. So we're interested in helping you with the problems that you face. We want to help you find the researchers that have expertise that can address the problems that you have that need solutions. And we're here to help you identify the best ways for you to work with researchers, how to establish that relationship. And as George said, another thing that we can do is help you to access the cutting edge facilities. They're here in this at Monash and in this precinct. And of course, we can help you leverage the federal and state schemes that exist for supporting R&D, and so we'd like to discuss those things with you. Okay, and that's all I have to say about. But please feel free to talk to me later about the center. Thanks.